Linear momentum of a system of particles. Let us recall that the linear momentum of a particle is defined as P is equal to mv. Let us also recall that Newton's second law written in symbolic form for a single particle is F is equal to dp by dt, where F is a force on the particle. Let us consider a system of n particles with masses m1, m2 till mn respectively and velocities v1, v2 till vn respectively. The particles may be interacting and have external forces acting on them. The linear momentum of the first particle is m1 v1 and for the second particle is m2 v2 and so on. For the system of n particles, the linear momentum of the system is defined to be the vector sum of all individual particles of the system. P equals p1 plus p2 till pn, which equals m1 v1 plus m2 v2 till mn vn. Comparing this with equation 7.8, P equals mv. Thus, the total momentum of a system of particles is equal to the product of the total mass of the system and the velocity of its center of mass. Differentiating equation 7.15 with respect to time, dp by dt equals m into dv by dt, which equals m into a. Comparing equations 7.16 and 7.11, dp by dt equals f external. This is a statement of Newton's second law of motion extended to a system of particles. Suppose now that the sum of external forces acting on a system of particles is 0, then from equation 7.17, dp by dt equals 0 or p equals constant. Thus, when total external force acting on a system of particles is 0, the total linear momentum of the system is constant. This is the law of conservation of total linear momentum of a system of particles. Because of equation 7.15, this also means that when the total external force of the system is 0, the velocity of its center of mass remains constant. We assume throughout the discussion on system of particles in this chapter that the total mass of the system remains constant. Note that on account of the internal forces, that is, the forces exerted by the particles on one another, the individual particles may have complicated trajectories. Yet, if the total external force acting on the system is 0, the center of mass moves with a constant velocity, that is, moves uniformly in a straight line like a free particle. The vector equation 7.18a is equivalent to three scalar equations px equals c1, py equals c2 and pz equals c3. Here px, py and pz are components of the total linear momentum vector p along x, y and z axis respectively. c1, c2 and c3 are constants. Figure 7.13a. A heavy nucleus radium splits into a lighter nucleus radon and an alpha particle, that is nucleus of helium atom. The center of mass of the system is in uniform motion. B. The same splitting of heavy nucleus radium with the center of mass at rest, the two product particles fly back to back. As an example, let us consider the radioactive decay of a moving unstable particle like the nucleus of radium. A radium nucleus disintegrates into a nucleus of radon and an alpha particle. The forces leading to the decay are internal to the system and the external forces on the system are negligible. So the total linear momentum of system is the same before and after decay. The two particles produced in the decay, the radon nucleus and alpha particle, move in different directions in such a way that their center of mass moves along the same path along which the original decaying radium nucleus was moving. If we observe the decay from the frame of reference in which the center of mass is at rest, the motion of particle involved in the decay looks particularly simple. The product particles move back to back with their center of mass remaining at rest as shown in figure 7.13b. In many problems on the system of particles, as in the above radioactive decay problem, it is convenient to work in the center of mass frame rather than in the laboratory frame of reference. In astronomy, binary, that is double stars, is a common occurrence. If there are no external forces, the center of mass of double star moves like a free particle as shown in figure 7.14a. The trajectories of the two stars of equal mass are also shown in figure. They look complicated. If we go to the center of mass frame, then we find that there are two stars are moving in a circle about the center of mass, which is at rest. Note that the position of stars have to be diametrically opposite to each other. Thus, in our frame of reference, the trajectories of the stars are a combination of 1. Uniform motion in a straight line of the center of mass, and 2. Circular orbits of the stars about the center of mass. As can be seen from the two examples, separating the motion of different parts of a system into motion of the center of mass and motion about the center of mass is very useful technique that helps in understanding the motion of the system. Figure 7.14a, trajectories of two stars S1 dotted line and S2 solid line forming a binary system with their center of mass C in uniform motion. B. The same binary system with the center of mass C at rest.